Okay, thank you. And for our next presenter, we have Amy.
Hi everyone, can you hear me?
Yes, we can hear you and see your presentation.
Okay, great, thank you.
You're a little bit quiet though.
Oh, okay, I'll talk. Wait, is this better?
That's better.
Okay, cool. So, good morning everyone. My name is Amy, and today I'll be presenting my research on COVID-19 detection and chest x-rays using transfer learning. So, the COVID-19 pandemic has greatly impacted countries worldwide with more than 20 million confirmed cases, and there is a need for quick and accurate screening methods. So the current main testing method involves using reverse transcriptase polymerase chain reaction, which can be time-consuming and costly. Chest X-ray scans can also be used as an alternative diagnosis technique and are faster, more widely available, and cheaper. However, X-rays require experienced medical professional to interpret, and as COVID-19 cases rise and hospitals become overloaded, there is an increasing need for computer-aided methods to improve the efficiency of diagnosis. So currently, research has been done to apply machine learning to detect COVID-19 from chest X-rays. And publications suggest that using transfer learning to build on pre-trained models can be an effective way for the classification of COVID-19. Transfer learning is especially applicable in this situation since we are working with a relatively small COVID-19 dataset. Instead of training a model from scratch, we can reuse a model such as the award-winning BGG, Inception, and ResNet networks that have already been trained on a huge image database, and then tailor them and apply them to our approach. New X-ray image data are being made constantly available, and the publications have not yet incorporated them into their models. So our goal is, or the purpose of this project is to design a machine learning model that integrates new image data and transfer learning to automatically detect COVID-19 from chest X-rays. My main focus is the selection of a base transfer learning model to help with COVID-19 diagnosis. The design should be accurate and also have low false negative numbers because misdiagnosing someone who actually has COVID-19 could result in increased spread of the virus. The model should also prevent overfitting and should allow for multi-class classification to allow medical practitioners to prioritize which patients to see first. Having interpretable results would also allow researchers and practitioners to understand the reason behind a particular prediction decision. The quantitative performance metrics that will be used to evaluate the model include the F1 score and accuracy, for which higher values would be better, as well as the number of false negatives, which we want to be as low as possible. To determine a model design, I built multiple classification models using transfer learning, trained and validated those models, then tested the model predictions, and used the performance metrics to evaluate the models. First, several models were built on the design shown in this diagram, using different pre-trained base model architectures. Each image was pre-processed to an image array and classified by the model as either no finding, thorax disease, or COVID-19. The model trains for 10 epochs, which is generally right when the training and validation accuracies start to converge, and that helps to prevent overfitting and allows for greater generalizability. A visualization technique is also applied for model interpretability. The models were then trained and validated using a dataset from a Kaggle challenge, which consists of a few different sources that are constantly updated. The dataset contains over 5,000 pre-labeled chest X-ray images, which were split into an 80% training set and a 20% validation set. Due to the imbalance of the classes in the dataset, the F1 measure was chosen as the primary metric for evaluating the models, as it more completely takes into account the precision and sensitivity of the model. The model accuracy was determined after the last epoch for training and validation. F1 scores and false negative values were also determined from the model validation. The false negative value was calculated from the sum of these two cells of the confusion matrix, where the actual label should be COVID-19, but the model predicts something else. The model was then tested on a separate image set containing over 1,000 images. The F1 score metric was applied to the testing set and was calculated based on 30% of these images. For model evaluation, preliminary testing was done on 5 base model architectures, which are shown in this slide. It was found that VGG16 and the DenseNet 121 architectures achieved high training accuracies of over 94%, and the VGG16 achieved the highest testing F1 score. To have a more in-depth study to inform my design decision, I've performed an additional 5 trials with 7 base models, including the new models highlighted, such as the second version of the ResNet 50 model. And I used the VGG16 results as a baseline. So the results showed that the ResNet 50 version 2 model and the exception model had one of the highest training and validation accuracies. However, high training accuracy during training and validation can sometimes be misleading because this could possibly show that the model is overfitting to that specific data set. It was also found that the DenseNet 121, ResNet 50, version 2, and exception models all have consistently low number of false negatives for the validation set. And with regards to validation and testing, these 3 models also achieved high F1 scores. The exception model also showed higher consistency than the other models, which suggests that the model may have a more reliable performance. And it was also noticed that the testing F1 score was generally lower than the validation F1 score, so further work can be done to minimize the discrepancy between training, validation, and testing. So overall, the ResNet 50 version 2, exception, and DenseNet 121 models achieved high performance based on the metrics. The exception model has also shown more consistency in its results. And a machine learning model that incorporates this architecture would allow for accurate multi-class classification with low false negative numbers and high generalizability and interpretability. After further refinements, this model can potentially be incorporated into a diagnostic workflow and help medical practitioners to detect COVID-19 from chest X-rays, which would save both time and lives. Other refinements, such as tuning the model parameters and performing image preprocessing to focus in on the lung areas, as well as increase dataset variation, can be done to help increase model performance and to avoid overfitting. The visualizations can also be further analyzed to better assess the model performance. So thank you for listening to my presentation. I would like to acknowledge the SR program, SIT, and my supervisor, Professor Chen, for this research opportunity, as well as many student researchers who helped me along the way. So thank you, and do you have any questions?
Thank you, Amy. Judges, whenever you're ready, please ask your questions.
Amy, thank you very much. Obviously very important, timely research that you're doing. In one of your closing slides, it looks like you're pointing to the exception model as being the most promising. Mm-hmm. So could you just, in simple terms, what is it about that model that makes it the kind of prime one of interest at the moment.
Okay, so based on the results that we achieved, you can see that the exception model has been performing well based on the performance metrics. So for both the F1 scores as well as the accuracy, it's been having high performance, and it is also really relatively consistent in its results. So you can see from here, this was for 5 trials, and you can see the error bars are relatively small for the exception model. So this would suggest that the exception model allows for more reliable results that are accurate and has low false negative numbers. So it would be a better model to incorporate into a general workflow to help with COVID-19 detection.
Good, thank you.
Yeah, I agree with my fellow judge here. This is very timely research, and thank you for doing this. You do mention that one of the concern looking at the data is to trying to reduce the false negative. I think that's a general public. We definitely appreciate that. So based on your study and comparison, did you see any of those models pay some special attention to try to, you may, what's the trade-off so that you may not have the highest F1 score, but if they very meticulously reduce this false negative, is that the model worth investigating further as well?
Okay, well, the F1 score actually, let me go back, takes into account both the precision and recall, which, as you can see here, it takes into account both the true, like the false positives and the false negatives, as well as the true positives. So the F1 score kind of finds a balance, sort of balance between those two measures. And for different models, sometimes it can be hard to find a balance between two measures, so you might not have a very high F1 score, but I guess for this case, for COVID-19 detection, we would still want to try and prioritize the number of false negatives, because we don't want to be misdiagnosing anyone who has COVID-19, as they can potentially cause more spread of the virus. But in the future, we would also want to take a look at other measures, because you also don't want to have a lot of people that don't have COVID-19 and the model predicts that they do have COVID-19, and that could potentially slow down the workflow as well. So you want to try and find a balance between those.
Okay, thank you for your answer. Again, I commend your the summer research participating in this very important research activity.
Thank you.
Okay, thank you everyone for your time. This concludes our podium session. Judges, if you have filled out the rubric through the online judging form, our judging director will be compiling the marks for the presenters soon. So again, thank you everyone for attending the session.
If you have any questions for presenters afterwards, we do have a questions for presenters channel that's accessible to everyone, and you can ask questions there. Thanks everyone, and thank you to judges.
Okay, thank you. Thanks for having us.
Great, thanks to everyone. Very impressive work. Thank you.